All right, let's talk about something truly mind-bending. We're diving into one of the biggest scientific stories happening right now, a brand new quantum processor from Google. It's called Willow, and it seems to have stumbled upon a mystery that questions the very nature of reality itself.
So let me just start with a question for you. What if a computer solved a problem that we thought was fundamentally impossible? I don't mean just really, really hard. I mean a calculation so gigantic that our best supercomputers would need longer than the entire age of the universe to figure it out.
Because, well, that's pretty much what just happened. You're seeing it right there. On one side, the estimate for a top-of-the-line classical supercomputer, 10 septillion years. And on the other side, the time it took Google's new Willow chip, 5 minutes. This isn't just a little faster. This feels like it breaks the rules of what computation is supposed to be.
The story really kicks off on December 9, 2024. A paper gets published in the journal Nature, and it quietly announces this result from the Willow chip. And for the physics community, it was like a thunderclap. I mean, just try to wrap your head around this number for a second. 10 septillion. That's a 1 with 24 zeros after it. Our entire universe, from the Big Bang until now, is about 13.8 billion years old. This number is 1 trillion times longer than that. It's so big, it stops being a real amount of time and becomes more of a philosophical concept, right? It means this cannot be done. And yet, Willow did it in the time it takes to make a cup of coffee.
Now, you might be thinking, hey, haven't we heard about quantum supremacy before? And you're right. Google's Sycamore chip made headlines back in 2019. But that was different. That was an impressive speed-up, sure, but critics argued that with smarter classical computers, we could close that gap. This is different. The gap is so unbelievably massive, it suggests we're not just playing the same game faster, we might be playing a different game entirely.
So how on earth is any of this even possible? To really get the mystery here, we have to pop the hood and understand the machine itself. How does a quantum computer think?
Okay, so your laptop, your phone, they all work with bits. A bit is simple. It's either a 0 or a 1, on or off. But a quantum computer uses something called a qubit. And the magic trick of a qubit is something called superposition, which basically means it can be a 0 and a 1 at the exact same time. And no, that's not a metaphor. It's a bizarre but very real feature of the quantum world.
And this is where it gets completely wild. The power grows exponentially. You have 2 qubits, you can hold 4 states at once. You get to 10 qubits, and that's over 1,000 states. But by the time you have Willow's 105 qubits, the number of states it can process at the same time is bigger than the number of atoms in the entire known universe.
And that leads us right to this central kind of haunting question in all of this. If you're doing more calculations than there are atoms in the universe to do them on, where is the work actually getting done? In a normal computer, it's happening in the silicon chips. But here, the math just doesn't add up. The books don't balance.
This apparent paradox has forced physicists to start seriously considering an explanation that, let's be honest, sounds like it's straight out of science fiction. The leading theory is that the computation isn't just happening in our universe.
David Deutsch, who is one of the absolute pioneers of quantum computing, has been saying this for decades. He argues the only explanation that really makes sense is that these machines are somehow tapping into and using parallel universes to get the work done. And after Willow, that idea is suddenly a lot harder to dismiss.
This is all based on something called the many worlds interpretation. The theory goes like this. Every time a quantum event could have more than one outcome, the universe actually splits. Every possible outcome happens, it just happens in its own separate branch of reality. So yeah, there's a universe where you wore a different shirt today. All of those possibilities are real.
And the main point here is that Willow is forcing scientists to actually grapple with this. It's not a dorm room debate anymore. As one researcher, Dr. Amara Okunkuo, said, we're basically building things that our current understanding of a single universe might not be big enough to explain.
And there's another piece to this that makes it all so much more concrete. A huge problem in quantum computing has always been errors. The more qubits you added, the more errors you got. It was a killer. But Willow seems to have cracked it. For the first time, as the system gets bigger, the error rate actually goes down. This is what makes a scalable, useful quantum computer seem like a real possibility, not just a lab curiosity.
But, okay, let's pump the brakes. Good science is all about skepticism. Is reaching into the multiverse really the only explanation for what's going on here?
So you've really got two main camps in this debate. On one side, you have many worlds, which says that the math describing all possible outcomes, the wave function, is literally describing physical reality. But the more traditional view, called the Copenhagen interpretation, says, no, it says the wave function is just a mathematical tool, a way for us to calculate probabilities. In that view, the computation is all happening right here, in our universe, by just being really, really clever with quantum weirdness. And here's the kicker, as physicist Dr. Jonathan Hartfield points out. Right now, both of these interpretations predict the exact same results in an experiment. So even though Willow's achievement is breathtaking, it doesn't actually give us the data to prove one side is right and the other is wrong.
So what's the bottom line? Willow has not proven that parallel universes exist. Let's be clear about that. But what it has done is yank this whole debate out of the philosophy department and drop it squarely into the middle of the physics lab. The question has become urgent and, frankly, unavoidable.
And when you really step back and think about it, you realize this moment fits into a historical pattern. It's the next chapter in the story of humanity's constantly expanding view of our place in the cosmos.
I mean, think about it. We once were sure the Earth was the center of everything. Then we realized, nope, we orbit the sun. Then we learned our sun is just one tiny star in a galaxy of billions, which is itself just one of trillions of other galaxies. Every step, the stage got bigger. Could the multiverse be the next step in that journey?
So why does all this matter? Well, if the many worlds idea is even close to correct, it means we have built a tool that literally operates across parallel realities. We're not just looking at the universe anymore, we're actively interacting with its deepest, weirdest, most hidden structure to get things done. It means reality is so much stranger and richer than we ever thought.
And that kind of leaves us with one last huge thought. We are now building machines that can ask questions so incredibly complex that our entire universe might not be big enough to hold the answers. So the real question becomes, are we?